High above the Gulf of Mexico, a colossal structure rises from the water, its steel legs piercing the ocean's surface like the stilted legs of a giant insect. This semi-submersible oil platform, designed to reach depths of over 20,000 feet, stands resolutely against the furious tempests that sweep the Gulf. Waves crash against its hull, some towering over 30 meters tall, yet the platform remains unwavering, as if it were anchored to the seafloor. How can such an immense structure withstand forces that would likely topple a skyscraper? It seems almost impossible, yet the engineering behind this resilience is a marvel of human ingenuity. Why is it that these massive oil platforms are engineered to survive waves bigger than buildings? The answer lies in the very design of semi-submersible platforms, which revolves around the concept of wave loading, depth, and buoyancy. By the end of this exploration, you will see that the deeper they sit in the ocean, the safer they become, utilizing the power of physics to protect both the structure and the crew on board. To understand the engineering behind such astounding resilience, we need to delve into the mechanics of ocean waves. When a wave passes through water, its energy decreases exponentially with depth. In simpler terms, the further you go beneath the surface, the less impact those waves have. This principle is key. The open ocean is home to chaotic forces, rogue waves, defined as waves that exceed the height of average waves by a significant margin, can reach staggering heights. The semi-submersible platforms like the Deepwater Horizon are engineered with submerged pontoons, which are designed to mitigate these wave forces. Each pontoon extends well below the surface, where the wave energy begins to dissipate. By staying at depths of about 10 to 15 meters, these platforms reduce the force acting on them by up to 50% compared to what they would experience at the surface. This remarkable engineering concept is grounded in the design principle that the most turbulent waves cannot reach below a certain threshold, making it safer. Take, for example, the infamous hurricane of 2005, Hurricane Katrina. Many oil platforms were tested against its fury. Some semi-submersible platforms remained intact despite facing substantial waves that exceeded 25 meters in height. This ability to withstand, and even thrive amidst, extreme conditions hinges on their structural design. They are not only buoyant, but intelligently shaped to help disperse the energy of massive waves. If we are discussing numbers, let's consider the 100-year wave design principle. Engineers utilize statistical modeling to determine the expected height of waves over a century, calculating that rogue waves can exceed 30 meters. This is not mere speculation, this is backed by rigorous mathematical modeling and historical data collection. The semi-submersibles are fashioned to endure waves far beyond ordinary experience, ensuring their collapse is almost impossible. Now, let's ponder a question that may seem obvious: why not construct these platforms entirely above the surface? Many people assume that the higher a structure stands, the more stable it will be. Instead, the physics of buoyancy and wave dynamics paint a different picture. By situating essential components below the water's surface, it stabilizes the entire platform. Imagine dragging a heavy heel downhill. The weight naturally keeps it anchored while you descend, rather than lifting it in the air where it can easily be overturned. Just as that heel buries into the earth, submerged pontoons sink deeper into the ocean, evading the worst of the storm. You might wonder if wave forces could still harm the platform. After all, they are colossal constructs designed for extreme conditions. Yet, the real trick is in how they distribute these forces. When a massive swell rolls toward the platform, it displaces the surrounding water, creating a bow wave. This wave ascends and, as it approaches, acts like a child playing on a trampoline finding that sweet spot where the bounce forces them upward. The energy from the wave dissipates around the platform, rather than focusing on any one structural component. Let's take a more recent example, the Eagle Ford oil field off the Texas coast, where advanced semi-submersible platforms successfully withstood hurricanes and powerful waves. This field has seen storm forces that sparked fears of destruction, yet the meticulously engineered platforms not only survived but continued to operate effectively. The bottom line is that engineers are way ahead of nature, utilizing a foundational understanding of physics to protect human investments and lives. Which of these machines would you least want to be standing next to? Tell us below in the comments. Additionally, consider the common misconception that moving closer to the surface would somehow enhance stability due to better visibility. However, it is effectively the opposite. The structure of the framework above water needs to bear immense weight where the buoyancy principles and balance come into play. This is where our earlier statement comes into play. Everyone assumes that rising higher is the answer to staying safe. But the truth is, the submerged design lowers the center of gravity, leading to an inherently stable platform. So, what's the twist? The actual trick behind the remarkable resilience of semi-submersible oil platforms lies in their geometric arrangement and depth within the ocean. Rather than striving to rise above the waves, they embrace their submersion, a fundamental engineering decision that enhances safety and stability, demonstrating that the ocean's ferocity can be met with wit and design genius. Reflect on this for a moment. A simple change in perspective reveals astonishing insights into our world. The cutting-edge engineering behind oil platforms serves not only to extract resources but holds vital lessons in how we might approach our designs and structures, adopting principles that respect natural forces rather than resisting them. As we conclude this analysis of semi-submersible oil platforms and their engineering marvels, it is crucial to appreciate the unseen world of physics, mathematics, and design elements that work in harmony to create something that can withstand nature's greatest challenges. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart. To further unravel the enigma of semi-submersible oil platforms, we need to explore how their design choices intertwine with the unpredictable nature of ocean waves. Waves are not merely water events, they are complex manifestations of energy and motion influenced by numerous factors. The forces acting upon a semi-submersible platform from the ocean's surface can be overwhelming, yet understanding the depths of those forces helps elucidate the engineering reasoning behind these resilient structures. Simply put, while most structures are subject to the lateral loading of waves, semi-submersible platforms distribute force differently due to their unique design. With their massive submerged pontoons, the platforms are not prone to the violent gyrations typical of surface vessels. Instead, they float upon a cushion of water, separated from the intensity of surface turmoil. If we liken a wave's upward crest to a kick from an angry ocean, the buoyancy of the submerged pontoons allows the platform to absorb the force through design rather than sheer strength. Furthermore, the physicist's understanding of buoyancy plays a pivotal role in how these structures float and function. The principle of buoyancy tells us that an object submerged in fluid experiences an upward force equal to the weight of the fluid it displaces. For a semi-submersible platform, the critical point is the size and shape of its pontoons, which affect the volume of displaced water and thus the supportive buoyant force. Designers meticulously calculate the dimensions of these pontoons to ensure they displace enough water even in turbulent conditions. A well-designed pontoon can measure up to 50 meters in length and potentially hold thousands of cubic meters of water, effectively converting wave energy from a destructive force into a manageable buoyant force. By employing effective hydrodynamic modeling, engineers are constantly revising and improving the shapes of these pontoons. This refinement leads to smoother interactions with incoming waves, enabling an astounding capability to maintain stability. For instance, modern semi-submersible platforms often feature a design dubbed X-bracing in their structure. This geometry mimics the shape of a truss bridge, providing additional strength and resistance against lateral forces. With this type of bracing, these platforms can manage the moment caused by waves, much like a bridge accommodates traffic load without collapsing. An exemplary demonstration of this resilience occurred during the North Sea storm of 2012. The Petrobras 10,000 semi-submersible platform successfully endured waves that reached over 32 meters high. The remarkable aspect of this incident was not simply the survival of the platform but, rather, its operational status immediately following the storm. Crews were able to maintain operations, thanks to the platform's capacity for energy dispersion during such extreme weather. Moreover, the engineering precision doesn't stop at the platform's design. There's also an extensive array of sensors integrated into these structures that allow for real-time data monitoring, including wave height, wind speed, and hull strain. Advanced telemetry systems communicate with engineers onshore, offering invaluable information to anticipate alterations in weather patterns and ocean behavior. This technology goes hand in hand with design. Systems are in place to predict and react to shifts in environmental conditions, ensuring safety and operational functionality are at their peak. Let us delve deeper still into the thrusts and pressures acting on these platforms. During the design phase, engineers conduct extensive simulations to model how various wave conditions will impact the structure. An essential aspect of this effort is the concept of dynamic amplification. This refers to how materials respond under sudden stress, which is crucial to consider given that waves can strike with unexpected ferocity. Through finite element analysis, engineers can identify potential weaknesses and dynamically optimize the design to withstand millions of cycles of pressure over their lifespan. Now, speaking of lifespan, the operational longevity of semi-submersible platforms is closely related to their maintenance routines and inspection protocols. These platforms are often designed for up to 20 years of service, factoring in the corrosive nature of saltwater and environmental impacts. Rigid adherence to maintenance schedules ensures that any sign of wear is identified and addressed promptly, preventing catastrophic failures. This operational discipline illustrates another layer of complexity in managing giant machines at sea. Many assume that with such formidable structures, everything works seamlessly, and therefore there's little risk of failure. However, it's interesting to note that engineering does not operate in a vacuum. The Deepwater Horizon incident in 2010 serves not only as a cautionary tale about operational protocols but also as a testament to the complexity of managing these platforms. The incident highlighted how human control measures, safety protocols and engineering design must all be seamlessly integrated to prevent disaster. The engineering of such platforms is inherently resilient, yet it must be complemented by vigilant operation to truly ensure safety. Returning to the fundamental question of why wave dynamics lead engineers to innovate continuously in seeking solutions that interpret nature creatively, think back on how they managed these incredible forces. A rogue wave, those tall and unpredictable surges that can strike suddenly, is estimated to be present roughly 1 in every 1,000 waves. They may throw an entire oil platform off balance if not carefully managed. However, semi-submersible platforms are often designed to withstand significant instances of asymmetry, the scenario where certain waves are larger, impacting one side more vigorously than the other. Using specialized software that models hydrodynamic impacts, engineers strategically calculate how the platform's design can compensate for such uneven forces. By creating structures that have variable buoyancy capabilities, they can alter their ballast as wave conditions change. Thus, either water or inert materials like cement can be introduced or removed from the pontoons for optimal performance during turbulent weather, thereby maintaining equilibrium and stability. To illustrate this in more vivid terms, imagine riding a bicycle. Shifting your weight from side to side helps maintain balance. The principles governing semi-submersible platforms employ a similar approach through active management of ballast. The insight engineers have gained through detailed analysis of real-world examples informs their ongoing advancements. Yet, with every engineering triumph comes ongoing innovation. Developers are constantly studying the potential for integrating sustainable energy solutions into platform operations. Some companies have begun exploring wind energy harnessing by integrating turbines into the structure of oil platforms, effectively using the location of their operations to capture additional eco-friendly power. This kind of integrative design represents a broader trend in further addressing environmental concerns while achieving essential energy production. As we reflect upon the resilience of semi-submersible platforms, we see that they are not only a marvel of engineering but a testament to the human spirit of innovation and adaptability. They compel us to recognize that our built environment can coexist with the powerful natural phenomena that surround us. While these platforms are designed to dominate the complexity of the sea, they also stand as monuments to the cooperative marriage of technology, physics, and biology. These structures bear the many lessons to be drawn as we continue seeking a delicate balance between progress and natural forces. In many ways, each oil platform is not merely a machine, but rather a critical part of a larger dialogue about how we relate to the environment. By appreciating the immeasurable complexities involved, we discover simple truths, that engineers have mastered the art of meeting nature's might with thoughtful resilience. Every giant machine hides one piece